All right, good. Any questions before we begin? I believe I'm recording now. All right, so let's study the last few things. So we talked about older stuff last time, references, classes, pointers, the heap. Let's talk about newer stuff this time. So one of the newer things that came after the last midterm was the idea of searching. Searching for something in something else. In a large data structure like an array or a vector, we want to know where something is, and we have to look through it. So searching is when you look for something inside of something else. Makes enough sense. And when you get to CSCI 41, you'll notice that, and you'll learn that there are a bunch of different things that you could search through, but in this class, we cared about searching through vectors and arrays. So pretend you had some sort of array where all the numbers are jumbled, and you wanted to look for a number in it. And you can see how this generalizes. You can make an array of some random struct, but the idea is the same. If you would like to find something in your array, like, I don't know, you're searching for the number 3, if your array is jumbled, you have no clue where that 3 might be, right? And you need to give back the index of it if it is there. So 0, 1, 2, 3, 4, 5, 6. So your job is to give back 4 in this case. This idea of looking through the array because you're not sure where it might be is linear search. Go through the entire array from left to right because you're not sure where the thing might be. It might be at the beginning or the end or somewhere in between. Okay, you return back the index of the value if you find it. And so you'll search through, you'll notice, hey, there's a 3. Let me give back the index that corresponds to it. Okay. So that is the idea of linear search. It's always going to work. Linear search has no problem on any kind of array because it's going to look at every value. If it's there, it will find it since it's looking at every value. No matter what the array looks like. It can even search for something that's not there. You'll go through, look at every index from left to right. You'll find that 42 is not in this array, and so you'll return -1. That's what you should return from linear search if you can't find it, because you're supposed to give back the index of where it is if you do find it. -1 is, of course, an index that never exists. Okay, so that's linear search. Any questions about that one? So linear search always works, but it can be slow if you have a special kind of array/vector. You can use binary search if your array is sorted. So instead of 8, 6, 7, 5, 3, 0, 9, let's sort those. So 0, 3, 5, 6, 7, 8, 9. If your array looked like this instead, it would be silly to look through every element. You could find things faster if you didn't. You play that game of looking in the middle for what you're trying to get. So num, let's say we're looking for 8. It'd be silly to go from left to right if you know that it's in order, because you know that if you look at an index and you look at that value, you know that everything to the left of it has smaller stuff. You know that everything to the right has bigger stuff, and that can help you cut off your search space. That's the fancy technical term. So you look in the middle, start your search in the very middle of your search space. The search space is the whole array to start. And then compare this, what you find there, to what you're looking for. And chop off half your search space because of it. So if you see 6 and you're looking for 8, you know that the only place in this array where the 8 could be is to the right. Okay, so you've just chopped off all of these elements right here. You've chopped them all off, and now you look through this. This is now your new search space. And then you look in the middle of that. It's like, all right, the middle, oh, cool, that's 8. Found it. Does that make sense? So you're always chopping off half until you find what you're looking for. And there it is. But maybe you were looking for, like, I don't know, 9 or something. This would be your search space. You look at 8 and be like, all right, it must be between here and here. Found it. Or if you're looking for 10, you're like, all right, it better be to the right of that, but there is nothing to the right of that. Your search space becomes empty, and you don't find what you're looking for. Okay, so that's binary search. Your search space starts out being the entire array /vector, and then you look left or look right. You chop off half the possibilities each try. Any questions about that before I go and implement it for you one more time? So let's see. Before I implement, I'm going to give you this example. I'm going to implement it for you. But before we do it, let's walk through an example of binary searching an array for 2. So let's say that we have this array, 2, 4, 6, 8, 10. And we're looking for the number 2. We know it's sorted, so we can use binary search. So here is how it works. So we're going to keep track of our search space through indices. We're going to have a low index and a high index. Low will start at 0, 1, 2, 3, and high will start at 4. Okay? And let's pretend, again, that we're looking for the number 2. So we start off, and we look at the middle index. So we average low and high to get the middle of our search space. 4 plus 0 over 2 is the number 2. So this is our midpoint. We'll call that mid in our implementation. Mid points here, and it tells us to look at 6. Okay, but we're looking for 2. How does 2 compare to 6? It's smaller, so that means I better look to the left. It's not 6, it's somebody over here to the left of 6. So I just chopped off half the search space. If it's anywhere, it's over here to the left. Okay, so that's the first step. And now we've changed our search space to be a bit smaller. So now low is going to say what it was, but high is now going to be over here. Let me draw that for you. So we had 2, 4, 6, 8, 10. We're still looking for 2. And so we cut off half of our search space. Low is still here, but high is now here. This is the largest index that could be the number that we're looking for. It's index 1. So low is 0 still, and high is now 1. Okay? And then we'll average together those. All right, what's the midpoint of this? 0 plus 1 over 2 integer division, so 0. Our midpoint then is index 0. And what do you know? When you look there, go to index 0, compare it to what you're looking for. Ooh, I found it. So I can return that index. Index was 0. That's my answer. And so I only had to look at 2 elements of the array to find this thing. I guess technically it would have been faster to find the 2 with linear search, but this will always be essentially 2 comparisons to find anything anywhere. That's the power of binary search. All right. Let's pretend that we weren't looking for 2, but we were looking for 1. We'll still get into this case. So let's say that we were looking for 1 instead. So we look at the 2. We look at index 0 because that's the midpoint. We'd see the 2, compare that to our 1, we'd be like, all right, it's not there, so I better search to the left of this. So low stays the same, but my high index is going to become -1. And that is going to give me an empty search space. When high passes low like that, when they become not what they should, when low is bigger than high for once, that means your search space was empty. There's nothing there to find. You return -1. That value that you're looking for wasn't there. Okay? Any questions about that strategy? Let's implement it together one last time. We'll use vectors. And what will we do? Here's how we'd like to use this vector. Int v equals 2, 4, 6, 8, 10. And see out the result of binary searching v for 2 should give me back index 0, and binary search v for 1 should give me back -1 because it's not there. Okay. So binary search returns an index, so it's int binary search. And it's going to take a vector, but we don't want to change it, but we don't want to copy it either. So we'll take it by constant reference. And we'll save the value that we're looking for, val2 search 4. Why not? Okay, so what we do is we start out our search space like this. index 0 is the low end, the last index is the high end. It could be anywhere at the beginning. So search space is initially the entire vector. So int low equals 0, and then int high equals the last possible index of v.size minus 1. And then we continue as long as we have a valid search space, look through it. So while low is less than or equal to high, as long as they haven't passed each other yet, we still have a valid search space. Like it's between index 3 and index 3, that's still valid. You better look at index 3 now. Okay? But at the start, it's going to be between like 0 and 4. Let's go in the middle of that. What's the middle index? Low plus high over 2. What's the value there? Let's compare it. All right? So compare what you see there with the value that you're looking for. So if the value at, or if the value that I'm looking for, let's do it this way. If that is less than what I see here, v at mid. So that means, that's essentially this case. I'm looking for a value that is smaller than what I see in my midpoint. So that means I need to go to the left. So that means my new search space better have its high right here, low can stay the same. High equals mid minus 1. Mid minus 1, because it's not here. At most, it's 1 before it. So look to the left. High equals mid minus 1. And the other way is symmetric. So else, if the value that I'm looking for is bigger than what I see here right now, that means I need to look to the right. So let's say we're looking for like the 10 instead. Then we'd see 6, and we notice, all right, it better be to the right, so I will change my low then to be mid plus 1. High can stay the same. That's my new search space. Look to the right. Low equals mid plus 1. Otherwise, if it wasn't less than, it wasn't greater than, it must have been equal to. We found it. And our job was to return the index of where we found it, and mid was that index. The at mid is equal to val to search for. Return mid. And this loop will continue as long as you have a search space to go through. If you're looking for something that doesn't exist, eventually your search space will not be valid anymore. Like high will be smaller than low, which makes no sense, which means you have nothing left to look through. If you get here, if the loop completes without having returned, you didn't find it. Return -1. We didn't find it. Sad face. Okay, so that is the implementation of binary search. Let's see if I can get it on one screen for you. Just barely. Okay, it's got to be like this. Are there any questions about it? All right, zooming back in then. And if we run it, we will hopefully find that it was correct. Yay, so 2 was at index 0, 1 was at nowhere, so -1. All right, and it'll find anything. So that is binary search. Let us next talk about recursion. So remember what recursion is. It's you have a problem, and you've noticed that you can find that same problem inside of itself in a smaller way. And that's also key. You can find a smaller version of that same problem inside of itself. So, for example, how am I going to program both of these? Apparently. Ooh, cool. All right. First example. Let's calculate x to the power of n. So we'll make a power function. So, for example, like you're taking x to the power of 5. Can you find a smaller power computation in here? I think I had you do this one already, right? You see x to the 4. That's the next smaller one. Also could have been here. There's x to the 3 as well. It's a couple times there. X squared, x to the 1. X to the 0 is always there because it's just 1. So there's our smaller computation. We can generalize this to, all right, if you want to calculate some variable to the power of n, where n is a whole number, of course, that's just equal to x times a 1 smaller power. And this is a recursive solution. X equals x times x to the n minus 1. And then you have to think about your base case, like what's the smallest power computation that you actually have an answer for immediately. You don't have to do any smaller ones. You can define like x to the 1 equals x. That's a potential base case, but you can do one better than that, because you can go all the way to 0. If anybody asks you for anything to the power of 0, the answer is immediately 1, and that's your base case. Okay? So, how do I want to do this? Okay. Let's do it this way. Recursion.cpp. And let's make it work like this. Cout pow for power, 2.0 to the 5th power. So we'll take doubles and return doubles, but the power needs to be a whole number, positive, non-negative number. So here is pow, double pow, int x, double x, to the power n, integer power n. All right, so this is going to return, how do I want to do this? It will return x to the power of n like this. And we can just read off our base case and recursive case to do the implementation. So when you're implementing a recursive function, you just have to figure out which case you're in. Am I in the base case? Am I in the recursive case? Because you have 2 potential rules to run for this particular example. So you're in the base case if n is 0. If you're trying to take x to the power of 0, the answer is always 1. Return 1.0. Why not? Base case. Otherwise, if n is not 0, hopefully the user didn't give you a negative power, because it'll never finish. But let's just pretend, let's assume we're in the recursive case. Otherwise, x to the n is equal to x times x to the n minus 1. And that, you can just immediately do that. Return x times, what is x to the n minus 1? Well, that's us. We're creating that. That's a smaller call to us. So that will work. You get to assume that it gives you back x to the n minus 1 properly. You just build up the final answer, and it will have worked. So return x times pow of x and n minus 1. All right, and so this will, in theory, calculate 2 to the 5th, 2, 4, 8, 16, 32 should be the answer. And it is. Any questions about this recursive function? So we're calling ourselves, we get to assume that the recursive call works, assume that that actually does the power computation correctly, it gives you x to the n minus 1. You just need to build up the original x to the n properly and return that. And if you do it, it will be correct, assuming the base case is also correct. Okay, next example, this will be fun. Let me prove to you that, let's do it like this, I guess. Let me prove to you that binary search is actually a recursive problem. So we've been doing it iteratively. We've been doing it with a loop. We've been using while, but you can use recursion to do binary search. If you think about it, what's the smaller problem that you find every time you're doing another round of binary search? What's getting smaller? Because something is getting smaller. It's the thing that you're looking through. It's always getting chopped off in half. It's smaller, which means recursion applies. You can make a recursive binary search because the search space gets smaller. Eventually, it will be so small that there's only one thing to look at, or it will be empty. Those are your base cases. Your base case is you found it in the middle, or your search space is empty, and you return -1. In order to do this, though, we have to add some extra parameters, because binary search, we have to specify our search space in the call at this point, because we don't want to give a new value for the vector. You could also do that, I guess. But we'll pass along low and high as parameters to binary search. We'll also need to return the result of the recursive call, because binary search will give back the answer, and if we want to pass off the problem to somebody else, we want to return what they gave us. This will make sense when I implement it. So here's the idea. Let me do my best to take this binary search and bring it in over here. So int binary search. So it's going to take the v value to search for. It's also going to take low and high now. And when you call it initially, here's what you do. The search space does have to be the entire vector. So let's see, how do I want to do it? Let's keep our example from down here. Let's keep these ones. Here's how you have to call it now if you're going to do it recursively and pass along low and high. So the initial search space better be 0 to v.size minus 1. That's the idea. Search for 2, search for 1, like we were doing. Then let's search for something in the middle of v, like 8. I also need v. Whee. Okay, so that's how you'll call it now. Binary search with the vector, with what you're looking for, and with your low and high indices, because these are going to change in the recursive calls. All right, so this will be interesting. So let's think about this. The base case for a recursive binary search. I guess the base case is when you have nothing left to look through. What's something where you have the smallest answer, you don't have to like binary search through any smaller array or vector? I would say that that's when you've ran out of things to look through. So the base case will be like this. If low is greater than high, if they passed each other and it doesn't make sense anymore, that's your base case. Search space is empty. There's nothing left to look through. You're expecting to find your value here, but there is nothing left to look at. Return -1. Otherwise, we're in the recursive case. Non-empty search space. And here's how you can do this. Let me bring all these back. It essentially makes sense. I don't have to indent it anymore. So again, we have low and high. They were given to us. What's the midpoint of our current search space? That still is the same. We need to compare it to what we're looking for. That's still the same. But searching to the left is now a call. It's a recursive call to us. I want to pass off the problem to myself. So high equals mid -1. How do you encode that idea when you call yourself? Well, I'm going to replace this with binary search. Call ourselves on v with the same value. Low stays the same, but high is now mid -1. That is us looking to the left. Mid -1. You see that? That's my call now. And this is a smaller problem. It will find the answer and give me back the location of the thing I'm looking for if it finds it, -1 otherwise. So this call returns an int. I was looking to the left. If this gives back an answer, it's the answer I want to give back. So I return whatever this tells me. That is how you transition to a recursive version. Are there any questions about this? So looking to the left involves making high mid -1. High is now a parameter. There it is. Change it to mid -1 and call yourself. Binary search through that smaller search space. And it'll find it. It'll give back the index or -1 if it doesn't exist. And we want to give that answer back as the solution to looking through the bigger array, because it only could have been over there. All right, so that's the idea. Looking to the right is the same business. High stays the same, but low becomes mid +1. That's looking to the right. Otherwise, you found it, and you do want to return that location. Mid is still the index you want to give back. You immediately have the answer if you found it in the middle of your search space. No matter if your search space is giant or small, if you found it, you found it. You don't need to do anything more. Otherwise, you need to look left or look right. And that is the recursive way of doing that. And so this case is now the base case handled. And so this is your recursive binary search. A little bit smaller, actually, because you don't need a loop. The looping is the recursion. So the base case is when your search space is empty. Return -1, nothing there. Otherwise, recursive case, look in the middle of your current search space between low and high. Go left or go right, depending. That's calling yourself. Return whatever they say. Otherwise, if you found it, return mid. Any questions about that? So that's pretty clean looking. I like it. Once you get used to recursion like that, that seems beautiful. And of course, it'll do the right thing. Looking for 2 is, of course, index 0. 1 doesn't exist, so it's -1. And 8 is index 0, 1, 2, 3. And so it prints it. Are we good on that? Examples of recursion. Let's see here. Next up on the list, we have makefiles. So makefiles are lovely because they let us just say once and for all how to compile our large, complicated program, and then we can just say make from then on, and it will compile it in the most efficient way possible. So let's remember what compilation means. Compilation versus linking and all that fancy stuff. So compilation is when you have one program, you have a single .cpp file, and you want to turn it into machine code. That's your .o. Compilation makes your .o's for you. And linking is when you have a bunch of compiled things, a bunch of CPP files, a bunch of library things, and you want to bring them together, combine them into a final executable program. That's what linking does. So here's the idea. So G++ does both for us, and that's why it's a bit tricky to teach, but I've told you the difference. The compiler is G++-C. That spits out .o files, object code for your single file that you're trying to create. Then you might have other .o files that you want to bring in that you previously compiled with G++-C, or you're trying to use some libraries like IOStream and Vector. Those have been pre-compiled for you by the standard library people. And then you can use G++ once more with the .o files to link them together to make a final executable file that you can then go and run, like /recursion. Okay. So that is the idea. That is makefiles in a nutshell. And that's the idea of separate compilation in a nutshell. We can use makefiles to make that happen. Okay, so separate compilation is when you use those .o files so that you don't have to recompile everything once just one file changed. Okay, so let me first split up our recursion program into a recursion library so we can use separate compilation, make a makefile for it. Everything will be beautiful. So I want to make, let's see, we could keep recursion.cpp here, but we'll only put the recursive functions in recursion.cpp. Let's make a main.cpp, and that will hold the main function, as I like to do. There's that. What else does the main file need? It needs IOStream, vector, namespace, standard. It can take all those. That's fine. You know, we might keep the vector. I might put that somewhere else. I'll deal with that in a second. Boop. So here's vector. Keep that around for just a second. We'll move it somewhere. So here's the main.cpp file. I'd like to make a recursion library, so I'm going to use recursion.cpp and then also recursion.h. So the .h file is going to store the declarations of all of these things. Make sure to include your header file guards so that you don't mess things up with infinite inclusion. But, gosh, get that out of here. Recursion.cpp, I'm going to copy and paste from that the declarations of all these recursive functions because that's what the header file should contain. So you put all your declarations here in your header file. And then this one needs to know about vectors. So that's where I'm going to put the vector, actually. I'm going to steal it from here, put it here. And in the header file, you cannot use namespace standard because this is getting copied and pasted when somebody includes it. So maybe that user did not want to include standard vector. So we'll call it like this. Standard vector int v. We have to spell it out. So these are the declarations of my functions. I will implement them in recursion.cpp. Customarily, you include your header file. So include recursion.h. And that will give us a few things. That'll give us the vector library. You can use namespace standard in any CPP file. That's fine. And then now we have the implementations of all of our functions. Cool. And then the main file needs to include our library, include recursion.h. That has the declarations of everything, just saying that they exist, and now it's happy. Okay, so I have, let's see. Oops. See if I can get all these on the same page for you. It's going to be a little tight. But we have main.cpp, which includes our library and uses it, uses POW, uses binary search. We have the header file, which declares all of the functions that we are providing in this library. Then we have the corresponding CPP file for this library, include ourselves for fun, and then implement all the functions declared there. Okay, so those are your header files and CPP files. We good with all that? And now to compile the whole thing, what you would like to do to use separate compilation, let's do it manually first. You'd say G++. Well, right now I just have, let me remove the compiled file recursion. You'll say G++-C on the CPP files. You'll say G++-C on main.cpp. That will make main.o. There it is. Then you'll say the same thing on recursion.cpp. That'll make recursion.o. There it is. And then finally, you'll link them together with one last call to G++. So you'll say G++ and then give the 2.0 files, main.o and recursion.o. And then you'll give what you want it to be called. Let's call it recursion again. Hit enter. And that has made the final executable file that I can then go and run. All right, and it runs just as before. So any questions about that before I make the makefile to automate all of that? So let me get rid of all those compiled files. Oops, did it not work? So we can do it all over again. Okay, let's make a makefile. So a makefile tells you how to build things. First of all, let's write down what we did. We had recursion.cpp. That was our file. We had main.cpp. That was our other file. We compiled them both to recursion.o and main.o. .o, main.o. Let me write that slightly better. And then, so that was the compilation process, compile. And then we want to link them together, those compiled things, into a final executable called recursion. You can call it whatever you want. Call it main, call it recursion. That's the linking stage down here. Okay, so the makefile tells us how to build what we're trying to build. Let's finally make the makefile. So the makefile is just a file called makefile with a capital M. That's all it is. And then you give rules. You give rules for how to build what you need to build. You got your targets, your requirements, and then the body of the rule after you tab over. So let's make a rule to create the .o file. So let's make main.o. You put a colon and then you list all the requirements. So in order to make main.o, I better have main.cpp in existence, because otherwise there's no way to get at main.o. And then I tab over, hit enter, and I give all the terminal commands to make main.o from main.cpp. So I'll say G++-C main.cpp. That will make main.o. Okay? So that's my rule. Same for recursion.o. Recursion.o requires recursion.cpp. And you just have to say G++-C recursion.cpp, and that will generate recursion.o. Finally, I'd like to make a final bigger program called recursion that's runnable and that links together the 2.o files. And so what I need is main.o and recursion.o. In order to link them together, they must exist. And the beauty of make, remember, is that if those .o files don't exist, but I'm trying to run this rule right now, it will go off and make those. It'll follow the chain of rules to get at what you really wanted, which is great. So how do you, using these 2.o files, create the final executable program? you link them together and call it the name of the rule, recursion. Okay? Any questions about this? So this is the make file. And I have gotten rid of all the compile files. So if I just say make recursion, it will run the recursion rule and compile everything that needs to be compiled. So it's going to look for main.o. It's going to notice that it doesn't exist, so it'll run the rule to make it. It calls g++-c main. There it does it. It'll do the same for recursion.o because it notices it does not exist yet. It runs it, makes it, and then you're off. Isn't that cool? Recursion.o. And then it finally is ready. It knows that it has these now. It can go and run the original rule for what you were trying to get at. Main.o, recursion.o, -o, recursion. Yay. And the beauty of this is it's separate compilation. So if I change one thing, like main, I don't know, let's search for 6 instead of 8, and I say make recursion again, it will recompile only the things that have changed. And also, because recursion is the first rule, you can also just say make by itself. It'll run the very first rule in the file. And so it notices, like, oh, I only need to recompile main. And then I'll link them together into recursion one last time. And now it finds the new answer. Isn't that cool? So let me change it again back to what it was. There we go. And again, make recompiles only the things that need to be changed and links them back together at the end. And now we have a new program. So that was the make file. Any questions about the make file? All right, a couple more examples. Let's do one on bitwise operations. We know and love them now, I hope. So here is the idea. So bitwise operations, they work on the individual bits of a number. Remember that if you have an int, it has 32 bits. So you have a big log int in binary form. It's a bunch of ones and zeros, ... all the way 32 bits long. So the bits are numbered in a special way. The least significant bit down here is bit 0. This is bit 1. This is bit 2. This is bit 3. All the way to up to bits 30 and 31 because it starts at 0. So 32 total. And you can perform operations on those individual bits with bitwise operations. So those work on the individual bits of a number. Usually you give 2. That one that flips them all just takes 1. So let me show you them all just in general. And or not XOR shift. I guess I should also, this whole time, I should have been showing you the little cheat sheet that I made for you. Because all these things are mentioned. So I put that in the lecture notes from before. Like pointers, recursion, find the problem inside of itself. Exceptions we'll get to. Bitwise operations run right now, and then make files. So please read this. It's helpful. The bitwise operations, they perform those logical operations on those individual bits of numbers. So like 0 and 1 makes 0. 1 and 0 also makes 0. The only time it makes a 1 is if they're both 1s for AND. Okay? So yeah, it just performs those operations on individual bits of a number. For example, you got your AND or not, XOR, and your shift. So let's give an example of AND. So AND is really good for checking if a bit is set. For example, if you have this number, here's my binary number, and I want to know, I'm not sure, if bit 2 is set. What you do is you AND by a number with zeros everywhere but there. You put a 1 right there in the bit that you want to check, and then you do bitwise AND. That's a single ampersand, right? So what that does is it checks whether or not that was set. So, of course, all these zeros are going to make the answer 0 for everybody else. But if this was a 1, this one will force it to still be a 1. If it was a 0, of course, it would make the whole thing 0. So what you do is you compare what you get after you do the AND. If the answer was 0, that means this bit that you were looking for was not set. Otherwise, if it was some number, which is going to end up being a power of 2, then it was, it was set. Okay, so that's and. OR is good for taking a bit and actually setting it, because you'll OR with a 1. Like if it was a 0 before, and you OR with a 1 in that location, it makes the answer a 1. So remember that. Let's see what else. Exclusive OR is good for flipping bits, because you can just exclusive OR with a 1. You got a 0, you exclusive OR that with a 1. That makes it a 1. You got a 1, you exclusive OR it with a 1. It makes it a 0. So that's fun. Remember, just go back to the tables, I think, would be a good way to study for this. There's definitely more that you can do, but this is a good start. Let's see. Yeah. So let us make 2 examples. Let's make a multiply by 2 to the n function. It takes a number in n and multiplies x by 2 to the power of n. And then we'll also make a flip bit function that takes a number and flips a bit in a given location, a given bit number. So for example, for our multiply by 2 to the n function, if we are given as arguments x being 3 and n being 4, then we want to calculate this, right? We want to multiply x by 2 to the n. So we want to give back 3 times 2 to the 4, which is equal to 3 times 16, which is apparently 48. I did the math ahead of time. 48. And the way that you do this is you think about it from binary. Remember that you start with 3, which is 1, 1 base 2. If you shift that, it's going to be a shift. If you shift that by 1, that's equivalent to multiplying by 2 to the 1. See that? That makes 1, 1, 0 in binary, which is 6. If you take 1, 1 in binary and you shift it left by 2, that makes 1, 1, and 2 zeros, which is going to be 12. That is multiplying it by 2 to the 2. So you see the pattern? If you want to multiply a number by 2 to the n, you shift left by n. That's going to be the answer. So very easy implementation. It's going to be one line. So cout, multiply by 2 to the n 3, 4. Let's take both of these because I'm going to have to implement them both anyway. So this gives back a new number. And this one also will give back a new number. And of course, because I copied it from PowerPoint, it does weird Unicode spaces for some reason. So, okay. That's so silly. Are you happy now? Better. Okay, so multiplying a number by 2 to the n, it's as simple as giving back x left shifted by n. It's beautiful. So this will indeed, let's have this do nothing, return x. Multiply by 2 to the n, 3, 4, that's just going to shift left 3 by 4. So there it goes, 48. So 3 times 2 to the 4 is 3 times 2, 4, 8, 16. 3 times 16, yes, that's 48. That's what it should be. So that's our multiply by 2 to the n. Any questions about that one? And then let's also do a flip bit example. So let me show you what you do. You do an exclusive OR. Remember that? So if you had this number, 1, 1, 0, 1, and you wanted to flip bit 1, which is this one, regardless of what it was, you'd XOR it with a number with zeros everywhere but the bit that you wanted to flip. And what it would do is preserve everything else, and then if they're different, it makes a 1. So it flipped it from a 0 to a 1 there. Cool. And then if you have the 1, 1, 1, 1, you do the same thing. If you do exclusive OR and you want to flip this same bit again, bit 1, then you would exclusive OR with 0, 0, 1, 0 once more, and you'd get 1, 1, 0, 1. Okay? And so that gives you the flipped bit one last time. And so these were the numbers that I wanted to flip. I wanted to flip this bit and this bit, so I would exclusive OR by this fancy number. And how do you get at this fancy number with a 1 in bit 1 and a 0 everywhere else? It's just, well, start with the number 1, which is a bunch of zeros and then a 1 at the end, and shift that left to whatever bit that you wanted. So 1 to the 1. 1 shifted left by 1. Gives you this number with zeros everywhere but bit 1. Okay? That's the answer. So to flip a bit, you take that number and you exclusive OR it with a number that is a 1 in the bit location that you would like to flip. And so I'm apparently passing along which bit to be the bit location that I want to flip. So let's do these two examples that I had here. This was 1, 1, 0, 1, which is 8 plus 4 plus 1, 13. Flip bit of the number 13, and we want to flip bit number 1 of it. And then that should make 15. If you flip it again, it should make it 13 once more. Yay, so 15 and 13. So it flips that bit in that location. So exclusive OR with a 1 just there, just in the one place that you want it, which is 1 left shifted to the bit location that you need it to be at. Any questions about that one? Okay, I've got one more example. Exceptions. So exceptions tell you when something bad happened. You got your try and your catch. Whee. So all these things. You throw exceptions. Exceptions are just values of any type. They could be objects, could be ints, strings, whatever. And then if you would like to handle exceptions, you put within a try some code that might throw an exception. And then you put some catch blocks to catch whatever kinds of exceptions you know right there how to handle. You could have multiple try catches. Some know how to catch this one thing, but others know how to catch this other thing. It all works out, right? So let's see. Exceptions. What do I want our examples to be? So yeah, let's do this. Let's make a let's change our recursive power function to actually throw an error when like you give it some bad argument, like a negative argument. We'll throw a runtime error. So let's do it that way. So let's try code that might throw an exception, catch certain exceptions. You usually catch them by reference. Give them a name. You can use them inside the body of the catch block. Runtime errors live in the standard except header. You'll throw them just like that. So without any further ado, let's take our recursive power function and add an exception to it. So I'll make a new file, exceptions.cpp, and then I'll take recursion.cpp as well and copy in our recursive power function. And then I'm also going to add exceptions to our bit flipping function, so I'll copy that in too right now. There we go. So that is a good start. And let's add a main function and stuff like that. And yeah, that should work. So first of all, notice the issue right now with power. We'll get to flip bit later. If we are given a negative power, we will stay in the recursive case until we run out of stack space and the program ends with a stack overflow. Because it'll try, like if you say x to the power of negative 1, it'll be like, all right, that's x times x to the power of negative 2. It'll go off and try and compute that. And it'll come here again. Like, all right, what's x to the negative 2? Oh, that's x times x to the minus 3. It'll keep on computing on and on and on forever. It'll never get to the base case because 0 is bigger than a negative number, and it keeps going down. So it's going to keep running and it would never stop. Okay, so for example, see out pow like 2.5 to the 5 works just fine, but 2.5 to like the negative 5 would be a stack overflow because it would never stop. It would never get out of the recursive case. Boop. And so you get a seg fault because you run out of memory. But the first one worked. So let's add an exception. Standard except. Let's also add strings because we're putting strings inside of our exceptions. If the user gives us a bad power, it's like if this n is negative, it won't work, right? We'll stay in our recursive case forever. It's not going to work out for our current implementation. So if n is less than 0, then let's throw a runtime error. And here's how you can make a runtime error. You just call the constructor, give it the string that you want to put inside of it, and you can use .what to get it back out. So throw a runtime error with some sort of helpful information, like can't take a number to a negative power. So that is the exception. So if the user ever tries to call pow with a negative exponent, we're going to throw this exception and we're not actually going to segfault, which is great. Recompile, rerun. Yay, it worked out. We threw the exception, but that stopped the program right now because we're not handling it. We're not catching it. So let's catch it. Let's try catch now. So here's a bunch of code that might throw an exception. Let's try to run it. Oops. Try to run it. Catch. And the one kind of exception that this code might throw that we know how to handle is a runtime error. So let's catch that by reference, call it E. So if the runtime error happened, you would handle it here, like clean up, do something different, but just for us, let's just print out e.what, which will give us back the string that we put inside of it, just for fun. You could, of course, do something fancier. Whee. So now, when we throw the exception, we're going to catch it here in main and handle it. Like, all right, we couldn't take a number to the negative power. That's the answer now. I couldn't get back something. I couldn't continue executing this line. All right, that's the try catch, and then the throw is up here. So you throw when the error happens, and then you let somebody else catch it. Any questions about that? Okay, so, all right. There's also an issue with our flip bit, so let's put an exception case in that one too. So you might be asked by the user to flip an invalid bit. So like cout flip bit, we had it like 15 bit 1, right? The user, like, okay, you can flip bit 2, those all exist, but what about -1? That bit doesn't exist. You can't shift left by -1. What's even going to happen? Let's see. Does it compile? Does it run? It gives back some weird answer because it makes no sense. Undefined behavior, probably. So we'd like to prohibit the user from asking us to flip a bit that doesn't exist. In an int, we can flip bits 0 to 31. Can't go outside of that. So let's throw an exception if the user tries to flip a bit that doesn't exist. That's a bit easier. So if, let's throw a string this time when the error happens, just for fun. You can throw any type. If which bit, the bit that I'm trying to flip, is invalid. So that means it's like negative, less than 0, or it's bigger than 31, because 31 is the last one you can flip, for an int at least. In either of those cases, you're outside the range, so let's throw an exception. Let's throw a string. Be like, I don't know, invalid bit, exclamation points. You can throw any type. You can throw 42 if you wanted to, but this alerts of the error, and it's not going to actually do a weird computation like it did here. Now it'll throw an exception. And we are going to get it, and oh no, it's over. So we didn't catch it, but at least we're getting the exception rather than the weird value now. So in the exceptional case, we throw a string, and now we can try catch. In main, let's pretend that's where we know how to handle this error if it occurs. So this is where we will put our code that might throw an exception, and then this code might throw a string. So let's mark to C++ that we know how to catch a string if it gets thrown as an exception. So catch string by reference S. So if something bad happened and we got a string, then cout, let's just cout the string. Obviously, you'd want to do some fancier kind of handling of the error, but this is just a simple example. And so now we get invalid bit. And remember what try catch does. Once an exception occurs, it jumps straight to the catch block and then the whole thing's done, because that kind of invalidates the rest of your computation most likely. So this line, this flip bit 15.2, never gets run, because the exception happens on the line above it. That flip bit call with 15 and -1 throws the exception. We are done with the try at that point. We jump straight to the catch and we're done with everything, because that kind of that invalidates our computation. Who knows? Maybe we needed that previous result to run this next result. Try it. C++ is not going to take any chances. It does not run any lines after the exception occurs. It jumps straight to the catch block, and that's it. Okay? Any questions about any of that? Exceptions? All right. So, yeah. Let's see here. What else? One thing that I wanted to remind you of, in addition to these other two things, is your accounts on the class server. They're not going to last for much longer. I'll have to clear them out to make room for the new students in the next semester. So if you want any code that you wrote on the class server, get it off using one of the methods I talked about previously. I can help you if you're having any trouble with that, but get it off by the end of finals week, I would say. Okay? That's the idea. So, yeah, any questions about anything we talked about today? That's essentially it. We have made it. You made it to the end of class. That's the last lecture. Thanks very much for putting up with me. And I guess all that I have left to say is show you memes and say good luck on the final. Let me know if you have any questions about anything. Remember when the final is going to be. Remember that it will be. Let me check on my other screen. Probably it's not going to let me log in. It looks like it's going to be on Tuesday. So our final will be on Tuesday. Tuesday at what time, though? This is all pre-planned for us by the school. So Tuesday at 3. So remember, it's not normal class time. It's 3, not 3:30. You show up here at 3 and take the exam. And we get until 4:50. All right, so Tuesday the 6th. Starts at 3. Okay, so meet in this room then. That is officially all that I have to say.